everybody, welcome back to another glorious maths video. In this video, we're going to be continuing a mini little subset of our abstract algebra series by continuing ring theory. Namely, we're going to be looking at subrings, ideals, and homomorphisms between these rings, okay? So we start off with a few basic definitions before immediately jumping into an important theorem. Okay, a motivating theorem for an important definition, okay? But first, let's just define what a subring is. So, you should know what a ring is, a commutative ring with unities, and all of that stuff from the last video. Okay? But in today's video, I'm going to assume that you know what that is. Okay? Now, as U, a subset of R, which is a ring, basically, is a subring if for all A and B we pick in R, okay, A and B being in U implies that A minus B is in U and A times B is in U. Okay? So, this is what a subring is. U, a subset of a ring R, is a subring if it satisfies this property. Okay? Now, a subfield is basically a subring that's a ring. So, say we have a field K, E, a subset of that field K, is a proper subfield, is a proper subfield of K if for all A and B in K, okay, A and B being in E, okay, implies that A minus B is in E, AB is in E, and if A is in E, that implies that A inverse is in E. Okay? Minus 0. Okay? So this is what a proper subfield is. Basically, I say proper because it has to be a subset of K to be a proper subfield. Okay? Doesn't have to be a subset of K to be a subfield of K. But if it's a proper subfield, it is a subset of K. Okay? So, now, an ideal, okay, is an ideal I is a subset of a ring R such that for all A, such that basically for all A and B in I, okay, A minus B is in I, and for all R in the ring and A in the ideal, R times A is in the ideal. Okay? So now we see that an ideal implies a subring, a subring implies an ideal, but an ideal does not necessarily imply a subring. For example, the integers are a subring of the set of rational numbers, but we see that it's not an ideal because, for example, if I pick a half in the rational numbers and 3 in the integers, we get 3/2, which is not an integer. Okay? So now we're going to take a look at a very motivating theorem, which will give us the definition of a principal ideal. Okay? Okay, so this is a theorem which might seem a bit random to you, but it's going to motivate the definition of an ideal generated by some elements A1, A2, A3, blah, blah, blah. And with that, the idea of a principal ideal, which we'll see later, has a close connection with divisibility. Anyway, the theorem states that if we let this finite subset of a commutative ring with unity, the set of A1, A2, blah, blah, all the way up to AN, and it's finite, that's important, okay? Then, this here, we'll call it RA1 plus RA2, da, 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 plus RAN, and this is equal to the set of all x1a1 plus x1 da, 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 such that these x1s, x2s, x3s are all in R. And this set here is the smallest ideal of R containing A. Now, the proof goes as follows. So, we just need to first of all verify that it's an ideal, and then it's logical from where that, then it's logical that this will be the smallest ideal containing A. So, if we pick some x1, x2, x3, all the way up until xn, and we have y1, y2, all the way up until yn in R, well then when we subtract those two, well then when we have x1a1 plus x2a2, plus x2a2 plus x3a3 plus all the way up until xnan minus y1a1 plus y2a2 plus y3a3 plus all the way up until ynan. And this is equal to, well, we have x1 minus y1 times a1 because of the distributive property of multiplication in a ring, because we have this times that and then that times that, we'll get what we originally had, minus x2 plus x2 minus y2 times a2 plus all the way up until xn minus yn times an. Okay? And this is clearly in RA1 plus RA2 plus RA3 plus all the way up until RAN. Okay? So, we see that for all A and B we pick in the ideal, when we subtract them, they'll also be in the ideal, which is one of the axioms for an ideal. Now, we have to verify the second one. So, if we pick R in the ring, and we have x1a1 plus x2a2 plus all the way up until xnan in RA1 plus RA2 plus all the way up until RAN. Okay, when we multiply them, we're left with R times, I'm just going to let this equal sigma for now because it's a bit tedious if I write the whole thing out again. R times sigma is equal to Rx1 times A1 by the associativity of multiplication plus, sorry, not comma, plus Rx2 times A2 plus all the way up until Rxn times An. And this is also clearly in, well now, sorry, I'm just going to call this capital sigma. And I'm just going to call this set for now sigma because I can't be bothered to write it out again. Okay? Now, they satisfy the axioms for an ideal, and, well, it follows that for any ideal we pick containing this A here, we're obviously going to have x1a, we're obviously gonna have this bad boy here, capital sigma, which we called it, popping out. No matter which x1, a1, x2, x3, forever, up until xn, we pick in R. So the ideal, let's call it I, is obviously going to contain this R, or R is going to be a subset of I, meaning that this R is the smallest ideal containing A. Talking, okay? Now, this theorem here, this proof, raises an interesting point. This here, and again, I'm too lazy to write this all out, and it's going to save time in the video, so maybe you'll be thankful, I don't know. If we call this right here sigma, okay? Well, definition, sigma is an ideal, sigma is an ideal generated by A, which is A1, A2, A3, all the way up until AN. Or, this is commonly denoted as this. Now, of course, this is equal to A1, A2, A3, all the way up until AN. But a principal ideal is an ideal generated by one element. Okay? Or it's written like this. So it's kind of like, you can kind of think of it as like a cyclic ring, kind of. We had cyclic groups, abstract algebra 1.4 or whatever. This is kind of like a cyclic ring, I guess. It's very similar, okay? And it has a close connection to divisibility, which we shall see. Okay, so this interesting connection to divisibility is that, well, if we have D, an integral domain, with U, a group of units, so the group of units U is equal to the set of all, let's say, U in D, such that there exists a V in D, such that so that UV equals the identity, multiplicative identity. Okay? Now, so U is a group of units. It holds that for all A and B in the integral domain minus 0, the principal ideal generated by A is a subset of the principal ideal generated by B, if and only if A divides B. So let's move on to proving that first. Proof of 1. Alright, let's call this I. Okay? Number 1 is, well, first assume that A divides B. If A divides B, that implies that there exists some U such that A equals U times B. Okay? Now, because the principal ideal generated by A is equal to A times D is equal to U B times D is a subset of B times D. Therefore, which is equal to the principal ideal generated by B. Okay? Therefore, A is a subset of B. Okay? Now, assume the other way round. A is a subset, if the principal ideal generated by A is a subset of the principal ideal generated by B, then there exists a Z such that A equals Z times B. Therefore, A divides B. Pretty simple. That's the proof of I. Now, to prove I, Captain, basically what you have to do, well, what does this equivalence relation here even mean? Okay, I'll leave it to you to prove this equivalence relation, but what it means is that, okay, so say for example we have a U and V in the units. If so A tilde B, if for some U and V in the units, A is equal to, U times B. Okay? That's what it means. Alright, so first of all, assume that A tilde B. If A, I'm just going to say equivalent to, I know that's not the way to say it, but, you know, it's a bit more natural than saying A tilde B. So A is equivalent to B implies that there exists some U, in capital U, the group of units, such that A equals U times B. And now, by the existence of inverses, because it's an integral domain, basically this means that A times U inverse equals B. Okay? Therefore, A divides B, B divides A, and by number 1, this implies that the principal ideal generated by A equals the principal ideal generated by B. Okay? Now, if, for example, we say that the principal of A is equal to the principal ideal generated by A is equal to the principal ideal generated by B. Okay? Well, what this means is that there exists some U and V in the integral domain such that U times A, for example, equals B, and V times B is equal to A. Okay, now, okay, so we picked the principal domain, the principal ideal generated by A equal to the principal ideal generated by B, which has this implication. And now, because U times V times B, is equal to U times V times B, by the associativity of multiplication, is equal to U times A is equal to B is equal to 1 times B, and by cancellation means that UV equals 1, meaning that U and V are units, meaning that A tilde B is equivalent to B. Okay? And this is the connection with divisibility. Now I'm going to define a ring homomorphism. Just like a group homomorphism, but they have 2 operations. So, if we let R and S be rings, a homomorphism phi, which takes you from R into S, okay, is a mapping such that phi of A plus B is equal to phi of A plus phi of B, and phi of AB is equal to phi of A phi of B. Okay? Okay, so now, we have some basic properties of these homomorphisms. Number one is that phi of the identity in R is equal to the identity in S. Okay? Why is this? Well, we have phi of A plus the identity in R equal to phi of A plus phi of the identity in R, which is equal to phi of A, okay, because this is just equal to A, okay? Now, using this fact here, we can say, by cancellation, by the existence of inverses, that this means that phi of the identity in R is equal to the identity in S. Okay, because we can easily just add negative phi of A on both sides, and there we go. Okay. Now we have that phi of negative R is equal to negative phi of R. Okay. Now, why is this? Well, we have that phi of R plus negative R is equal to phi of R plus phi of negative R, which is equal to, remember this is phi of the identity in R, which is equal to the identity in S. So it follows that phi of negative R is the additive inverse of phi of R, so it follows that phi of negative R is equal to negative phi of R. Okay? And these are some elementary properties of homomorphism, you know. But it's always helpful to know extra definitions, just in case, you know. So, these definitions are all closely linked to homomorphisms. A morphism is a homomorphism is a homomorphism which is injective. Okay? An isomorphism is a bijective homomorphism. And I'm just going to write it like that because writing out homomorphism is really tedious. Okay, and I don't want to waste ink, especially in these strange times where getting markers is hard. Okay? And for a lot later when we study Galois theory, it's good to know that an automorphism is an isomorphism such that the mapping such that it goes from the ring R to R, to itself, basically. Okay? And that's it for this video. Hopefully you guys enjoyed. Stay tuned for the next abstract algebra video, where I'm going to be continuing a little bit of ring theory. See you then. Goodbye.